The universe is not what it seems. We look up at a familiar night sky, but the reality behind it is filled with forces and phenomena that fundamentally contradict our basic understanding of physics. This journey explores 25 cosmic mysteries that defy all explanation, from an invisible energy tearing space apart to particles connected across billions of light years. You will gain a new perspective on the deepest secrets of the cosmos, revealing just how much we have yet to understand. Why does most of the universe remain completely invisible? And what happens to reality inside a black hole? How many of these cosmic puzzles do you believe we will ever truly solve? Our cosmos is not merely growing larger, it is fleeing from itself at an ever-increasing speed. This astonishing discovery came from watching the death throes of massive stars billions of light years away. Astronomers observed that the light from these distant supernovae was fainter than it should have been, a clear sign they were farther away than anyone had predicted. The only explanation was that the very fabric of space-time is stretching apart, and the rate of this expansion is not slowing down due to gravity, but accelerating. An invisible repulsive force, which we call dark energy, is pushing the universe apart. This force is so dominant that it makes up about 68% of all the energy in the cosmos. It is the majority of everything, and we have no idea what it is. One possibility is that it is an innate property of empty space itself, a concept Einstein once proposed and then discarded as his greatest blunder. Empty space, according to this idea, is not nothing. It has a fundamental energy that causes it to push outward. Another theory suggests it is a dynamic field, nicknamed quintessence, that changes over time. Regardless of its true nature, the implications are profound. If this acceleration continues unchecked, the fate of the universe is a cold, lonely, and dark one. Galaxies will be pushed so far apart that their light can never reach one another. The cosmic sky will go black, and the universe will essentially die of heat death in what scientists call the Big Freeze. How can the fundamental nature of reality be dictated by something we cannot see, touch, or directly measure? This mysterious pressure in the vacuum of space is the first and greatest puzzle, a force that defies gravity and our understanding, setting the stage for another, equally baffling, invisible component of the cosmos. But if dark energy is the force pushing the cosmos apart, what is it that holds it all together? We find the answer in another, equally invisible component, a ghostly presence that forms the very scaffolding of the universe. This is dark matter. Picture a galaxy spinning, its stars whirling around the center. According to the laws of gravity, the stars on the outer edges should be moving much slower than those near the core, just as Pluto orbits our Sun far more slowly than Mercury. Yet when astronomers measure these galactic rotations, they find something astonishing. The outer stars move just as fast as the inner ones, as if the entire galaxy is embedded within an enormous, invisible sphere of mass, a halo of something we cannot see. This missing mass was first noticed by the brilliant and often contentious astronomer Fritz Zwicky back in the 1930s. He observed galaxies within a distant cluster moving so quickly that they should have flown apart, yet they remained bound together. He concluded that some unseen form of matter, which he called dunkle materie, must be providing the extra gravitational glue. This dark matter does not interact with light in any way. It does not shine, it does not absorb, and it does not reflect. It is completely transparent, passing through our world and even our bodies without a trace, its presence known only by the relentless tug of its gravity. Without this invisible framework, galaxies would never have formed in the first place. After the Big Bang, the slight gravitational pools created by dark matter were what attracted ordinary matter, the stuff of stars and planets, allowing it to clump together into the vast structures we see today. So what is it made of? The leading candidates are hypothetical particles with names straight from science fiction. Weakly interacting massive particles, or WIMP, are heavy particles that barely interact with normal matter. Or actions which are incredibly light and could be streaming through the universe in vast numbers. Scientists have built extraordinary machines to find them, from the colossal Large Hadron Collider that smashes particles together in hopes of creating a speck of dark matter, to sensitive detectors buried deep underground in old mines, shielded from cosmic rays, waiting for a single, elusive dark particle to bump into an atom. So far, the detectors remain silent. We are surrounded by this cosmic phantom, a substance that makes up about 27% of everything that is, and yet it refuses to reveal its identity. This fundamental gap in our knowledge forces us to ask an even bigger question. If we do not know what most of the universe is made of, how can we possibly know its true shape or predict its ultimate fate? The very shape of the cosmos dictates its final destiny, a geometry written on the largest possible scale. Our best measurements from missions like the Planck satellite paint a startlingly simple picture. On the grandest scales, the universe appears to be geometrically flat. This is not flat like a tabletop, but in the cosmic sense. It means parallel lines will never meet, and the angles of a triangle will always add up to 180 degrees. This flatness is a critical clue, a delicate balance between the density of all matter and energy and the expansion rate set by the Big Bang. If the universe had been just slightly denser, its own gravity would have curved space inward, creating a closed universe, finite and without a boundary, much like the surface of a balloon. Such a cosmos could eventually stop expanding and collapse back in on itself in a fiery big crunch. If it had been less dense, space would be curved outward in an open, hyperbolic shape, destined to expand forever into a vast, thin emptiness. The fact that we observe a flat universe is like a pencil balanced perfectly on its point, a state so finely tuned it demands an explanation. This flat geometry, combined with the relentless push of dark energy, currently points toward one particular future, the Big Freeze or heat death. In this scenario, the expansion continues forever. Galaxies drift apart beyond the cosmic horizon, stars slowly burn out, black holes evaporate, and all activity grinds to a halt across an unimaginable expanse of time. The universe becomes a cold, dark, and uniform sea of decaying particles. But is this fate truly sealed? The answer depends entirely on the nature of the dark energy that drives the acceleration. If its strength remains constant, the Big Freeze seems inevitable. But if it changes over time, anything could be possible. The universe could still tear itself apart in a big rip, or perhaps dark energy could reverse its effect, pulling the cosmos back together. As the renowned cosmologist Martin Rees once noted, the universe is not only queerer than we suppose, but queerer than we can suppose. Our uncertainty about the cosmos's grand structure and its ultimate end forces us to look back to the very beginning, to the moment everything was created in a single, incomprehensible event. Yet the very existence of this cosmic scaffolding and the fate it implies forces us to confront the ultimate question, the moment of creation itself. The Big Bang is the foundational story of modern cosmology, the event that set everything in motion. All the matter and energy we see today, the entirety of space and time, was once compressed into an unimaginably hot, dense state. A singularity where the known laws of physics simply ceased to function. Then, in a cataclysmic flash, it began to expand and cool, giving rise to the universe we inhabit. The evidence for this event is overwhelming, from the redshift of distant galaxies showing the universe is still expanding, to the faint afterglow of the heat from that initial explosion, the cosmic microwave background radiation that fills all of space. But for all its success, the Big Bang Theory leaves the most profound questions unanswered. What actually triggered this event? What, if anything, existed before it? Some theories attempt to push our understanding back into those first fleeting moments. Cosmic inflation proposes that a fraction of a second after the beginning, the universe underwent a brief period of exponential, faster-than-light expansion. This sudden growth spurt would have smoothed the cosmos to the flat geometry we observe and planted the tiny density fluctuations that later grew, under the influence of gravity, into galaxies and clusters of galaxies. Yet inflation itself is a mechanism that requires a trigger, leaving the initial cause still shrouded in mystery. Other ideas are even more radical. The cyclic model suggests our universe is just one in an endless series, with a big bang followed by expansion, then a contraction into a big crunch, which then triggers the next big bang in an eternal cycle. The Multiverse Hypothesis posits that our Big Bang was merely a bubble inflating within a vast, eternal meta-universe, one of countless others in an infinite cosmic foam. The renowned physicist Stephen Hawking offered a perspective that challenges the question itself. He argued that asking what came before the Big Bang is like asking what is north of the North Pole. In our current understanding, time itself began with the Big Bang. The concept of a before may have no meaning, as there was no time for anything to exist in. The initial singularity represents the absolute boundary of our knowledge, a point where our current physics breaks down. To peer beyond it, or to understand the moment of its birth, we likely need a theory of quantum gravity, a framework that can unite the vast scale of general relativity with the tiny, probabilistic world of quantum mechanics. String theory and other candidates attempt this monumental task, suggesting that at the very beginning, the universe may have existed in a state of higher dimensional vibrations, a cosmic symphony from which space, time, and matter all emerged. As we grapple with the mechanics of the universe's birth, we are inevitably drawn to a deeper, almost philosophical puzzle. Why is there something rather than nothing? This question is intimately tied to another great cosmic imbalance that occurred in those first moments, a fundamental asymmetry that allowed our world to exist. For every particle of matter created in the Big Bang, a matching particle of antimatter should have been created. Matter and antimatter are opposites in charge, and when they meet, they annihilate each other in a pure flash of energy. If nature were perfectly symmetrical, all the matter and antimatter produced in the early universe should have completely destroyed one another, leaving behind a cosmos filled with nothing but light. Yet here we are in a universe made almost entirely of matter. Some slight violation of symmetry in the laws of physics must have favored matter over antimatter, allowing a tiny, 1 in a billion remnant to survive the great annihilation and form everything we see. What was that primordial preference, and what force decided that something would win over nothing? The answer lies hidden in the behavior of the most elusive particles in existence. That perfect symmetry at the dawn of time should have been our undoing. For every particle of matter born from the fire of the Big Bang, an identical twin of antimatter must have been created. Think of them as perfect cosmic opposites, identical in mass but with opposite electrical charges. When a matter electron meets its antimatter counterpart, a positron, they do not just cancel each other out, they vanish in a pure, violent flash of energy, returning to the void from which they came. In a perfectly symmetrical universe, this should have been the fate of everything. all the matter and all the antimatter should have mutually annihilated, leaving behind a lifeless, expanding cosmos filled with nothing but fading light. There should be no galaxies, no stars, no Earth, and certainly no us. The fact that you exist to ponder this question is proof that the universe is not perfectly symmetrical. Something tipped the scales. 1 out of every billion matter particles somehow survived the Great Annihilation. That tiny, precious surplus is everything we see, everything we are. This is the mystery of the missing antimatter. Physicists call the necessary imbalance CP violation, a subtle flaw in the laws of physics where particles and their antiparticles do not behave in perfect mirror image. We have found this violation in the lab. In giant particle accelerators like CERN, scientists smash particles together at nearly the speed of light and study the debris. They have observed certain exotic particles like kaons and B mesons decaying in slightly different ways than their antimatter counterparts. It is a real, measurable effect, but here is the catch. The amount of asymmetry we have measured is far, far too small to account for the overwhelming dominance of matter in our universe. It is like finding a single dropped coin when an entire treasure chest has gone missing. So where did the rest of the antimatter go? The hunt for answers pushes physics to its limits. Some theories look to the ghostly neutrino. If these elusive particles are their own antiparticles, they could have triggered a process that filtered out more matter in the early universe. Other ideas, like supersymmetry, predict a whole new family of particles whose interactions could have provided the necessary cosmic bias. Every experiment brings us closer, yet the definitive answer remains hidden. This is not just an academic puzzle. The very existence of the cosmic structures we see, from the grandest spiral galaxy to the smallest planet, hinges on this primordial preference. It forces us to confront an even deeper enigma. Why are the rules of the game so exquisitely fine-tuned? The fundamental constants of nature, the numbers that govern the strength of forces and the masses of particles, appear to be perfectly calibrated for a universe that can eventually support life. The delicate balance that allowed matter to survive is just one piece of a much larger puzzle, a cosmic conspiracy of numbers so precise it seems to whisper of intentional design. The fundamental constants of nature, the unchangeable numbers that dictate the strength of gravity, the power of the nuclear forces, and the very mass of an electron, are all set to values that appear perfectly calibrated for life. If any one of these numbers were different, even by an almost negligible amount, the universe as we know it would not exist. If the force of gravity were slightly stronger, the universe would have collapsed back on itself long before stars could form. If it were slightly weaker, matter would never have coalesced into galaxies and planets. The cosmological constant, which governs the strength of dark energy, is fine-tuned to an almost incomprehensible degree. Nobel laureate Steven Weinberg calculated that its value is precise to 1 part in 10 to the power of 120. That is a 1 with 120 zeros after it, a number so vast it exceeds the total number of particles in the observable universe. This is not like winning the lottery, it is like winning the same lottery 1 trillion times in a row. This staggering precision is known as the fine-tuning problem, and it forces a profound question. Why is the universe so hospitable to conscious life? One compelling answer is the anthropic principle, which simply states that we can only observe a universe that is capable of producing us. If the constants were not just right, we would not be here to notice. For some scientists, this is a logical, if unsettling, conclusion. It means we should not be surprised by the universe's hospitality, because our existence is the very proof of it. Others find this explanation deeply unsatisfying and propose a radical alternative, the multiverse. In this view, our universe is just one bubble in an infinite cosmic foam, a single ticket in a lottery with an infinite number of draws. In most of these universes, the constants are wrong and they remain dark, empty, and lifeless. But by pure chance, in a few, the numbers line up perfectly, and in those rare oases, life emerges and wonders at its own luck. This debate sits at the boundary of science and philosophy. Does fine-tuning point toward a deeper, undiscovered law of nature that necessarily produces life-friendly conditions? Or does it suggest something more, a cosmic architect who set the dials? There is no consensus, only the humbling reality of the numbers themselves. This fine-tuning does not just affect the possibility of life on small planets, it governs the grand architecture of the cosmos. The precise strength of gravity and dark energy directly influenced how matter clumped together to form the vast web of galaxies and the immense gravitational anomalies we detect, like the Great Attractor, a mysterious region of space pulling thousands of galaxies, including our own Milky Way, toward it. The universe seems rigged for complexity, from the largest structures to the smallest particles. But what if this intricate cosmic balance is not a feature of reality, but merely an illusion? What if the very laws of physics are not constant, but change over time or vary from one place to another, rewriting the rules of the game across the expanse of space and time? The universe's fine-tuning for complexity is written into its largest structures, a cosmic architecture governed by gravity and shadow. But even our own galaxy is not a stationary island in this vastness. It is caught in a relentless river of motion, pulled by a force we cannot see. Our entire Milky Way, along with its neighboring galaxies, is racing toward a specific point in the void at a staggering speed of over 1 million miles per hour. This destination is the Great Attractor, a gravitational anomaly of almost unimaginable power located in the direction of the constellations Centaurus and Norma. Its discovery came not from a direct image, but from a map of cosmic peculiar velocities. Astronomers noticed that the motion of galaxies, including our own, could not be explained by the uniform expansion of the universe alone. Something else was tugging at them, a deviation from the smooth Hubble flow that pointed toward a colossal, unseen mass. The true nature of this region remains elusive because it lies directly behind the crowded plane of our own galaxy, in an area astronomers call the zone of avoidance. Here, the gas, dust, and brilliant stars of the Milky Way's central bulge create a thick cosmic fog, blocking our view of the universe beyond invisible light. It is like trying to see a distant mountain range through a blinding sandstorm, but scientists have used instruments that can peer through this veil, like radio and X-ray telescopes, to glimpse the structure hidden behind the glare. What they infer is a gravitational heart with the mass of tens of thousands of galaxies, a focal point for the motion of our entire local supercluster. Is it a single, unimaginably dense knot of dark matter, or is it a massive confluence of galaxies, a supercluster whose true extent we are only beginning to map? Some researchers believe the Great Attractor itself may be just a waypoint, a local ripple in a much larger current. The even more immense Shapley supercluster, located hundreds of millions of light-years beyond, may be the ultimate source of the pull, a gravitational heavyweight that is drawing us and the Great Attractor toward it. This reveals a cosmos not of random scatter, but of immense flows and currents, where galaxies move in streams toward the densest concentrations of mass, most of which is invisible dark matter. The Great Attractor is a humbling reminder that we are not still, but passengers on a cosmic voyage, swept along by forces whose origins lie in the deepest shadows of space. This grand-scale influence of the unseen has a bizarre parallel in the microscopic world, where particles themselves seem to defy the very concept of location and communicate in ways that challenge our understanding of reality itself. This same defiance of classical physics echoes in the behavior of the smallest particles, a realm where logic seems to break down entirely. Two particles can become inextricably linked, their fates intertwined in a bond that distance cannot break. This is quantum entanglement. When you create a pair of entangled particles, their properties, like spin or polarization, remain connected. Measure the spin of one particle, and you instantly know the spin of its partner, even if that partner is now on the other side of the galaxy. There is no signal traveling through space, no exchange of energy, just an immediate, silent correlation. Albert Einstein was deeply troubled by this, famously dismissing it as spooky action at a distance. He believed it pointed to a flaw in quantum theory, suggesting there must be some hidden, local variables that predetermine the particle's states. For decades, this was a philosophical debate. Then the physicist John Bell devised a way to test it. His inequalities set a mathematical boundary. If local hidden variables existed, the results of certain experiments would fall within that boundary. When scientists finally performed these experiments, the results were unequivocal. They violated Bell's inequalities, proving that no local, hidden theory could explain the behavior. The spooky action was real, so how does it work? The truth is, no one knows for certain. The measurement of one particle does not send a message to the other. Instead, it seems the two particles are not truly separate entities at all, but part of a single quantum system. They share a single existence, a single wave function, and observing one part of that system simply reveals a property of the whole. This does not allow us to send faster-than-light messages, a rule protected by the no communication theorem. You cannot force one particle into a specific state to send a signal, because the outcome of your measurement is always random. You only see the correlation after the fact when you compare notes with someone holding the other particle. This profound interconnectedness is not just a laboratory curiosity. It is the engine behind emerging technologies like quantum computing and unbreakable quantum cryptography. Yet the fundamental mystery remains. What does this say about the nature of space and time? Entanglement suggests that separateness may be an illusion, that the universe is woven together with threads of instantaneous connection that operate beneath the fabric of space-time. This quantum weirdness, so baffling on the microscopic scale, finds a terrifying parallel in the most extreme environments the cosmos has to offer. The bizarre rules of quantum entanglement seem to dissolve the very idea of distance, but there is a place in the cosmos where the concept of space and time is not just bent but utterly shattered. Black holes are regions where gravity becomes an inescapable prison. Their boundary, the event horizon, marks the point of no return. Cross this invisible threshold, and the gravitational pull becomes so overwhelming that escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing, not even a single photon, can ever come back out. The black hole's interior is a complete mystery, but at its very center, according to general relativity, lies the singularity, a point of infinite density where the laws of physics as we know them simply cease to apply. We have moved from theory to observation. The Event Horizon Telescope collaboration gave us the first breathtaking image of the supermassive black hole at the heart of galaxy M87, a fiery ring of light orbiting the darkest shadow in existence. Yet this observational triumph only deepens a fundamental theoretical war that has raged for decades. It is a conflict between the two pillars of modern physics, general relativity and quantum mechanics, and the battlefield is the black hole itself. The problem is information. Quantum mechanics states as an absolute principle that information cannot be destroyed. Every particle that falls into a black hole carries information about its properties, its mass, its spin, its quantum state. If the black hole simply exists forever, that information is trapped but technically still exists in the universe. However, Stephen Hawking made a stunning calculation in the 1970s. He showed that black holes are not truly black. Due to weird quantum effects at the very edge of the event horizon, they slowly radiate energy, a faint whisper of particles now known as Hawking radiation. This process causes the black hole to lose mass and, over astronomical timescales, completely evaporate, vanishing from the universe. This creates the information paradox. If the black hole evaporates into a random, featureless bath of radiation, what happened to all the information about the stars, planets, and particles that fell in? Was it truly erased from reality, violating a cornerstone of quantum law? This paradox has forced physicists to propose radical solutions. One of the most profound is the holographic principle. It suggests that all the information about what falls into a three-dimensional black hole is not lost inside, but is somehow encoded on its two-dimensional event horizon, like a cosmic fingerprint smeared across the surface. The entire interior could be a holographic projection from that data-rich boundary. An even more violent idea is the firewall hypothesis. It proposes that the event horizon is not an empty, peaceful threshold, but a searing wall of high-energy particles that would instantly incinerate any object falling through, resolving the paradox by destroying the information at the boundary in a way that is consistent with quantum theory, but utterly violating the gentle spacetime curvature predicted by Einstein. The debate is far from settled. Recent work in string theory and something called the ADS/CFT correspondence provides mathematical frameworks where information can escape during evaporation, perhaps encoded within the Hawking radiation itself. The study of black holes is more than an academic exercise. It is a direct probe into the nature of reality, forcing us to reconcile the very large with the very small. As we ponder these monstrous engines of gravity, we are drawn to the one that lies closest to home, a silent giant lurking in the chaotic heart of our own galaxy. At the chaotic heart of our own Milky Way, a silent giant holds court. This is Sagittarius, a star, a supermassive black hole with a mass 4 million times that of our Sun. It is not alone. Astronomers now believe that nearly every large galaxy has one of these behemoths at its center, a gravitational monarch whose immense power shapes the destiny of its entire domain. We detect them not by seeing the black hole itself, but by watching its influence. Stars are seen whipping around an invisible point at dizzying speeds, tracing elliptical orbits that reveal the presence of an unseen, monstrous mass. In other galaxies, we see quasars, the intensely bright cores of active galactic nuclei, where a supermassive black hole is actively feeding. As vast amounts of gas and dust spiral inward, forming a searingly hot accretion disk, the friction and magnetic forces generate so much light that a single quasar can outshine its entire host galaxy. These cosmic engines are proof of the black hole's presence and its transformative power. The greatest puzzle is how they grew so big so fast. We see fully formed supermassive black holes, billions of times the Sun's mass, shining as quasars when the universe was less than 1 billion years old. How did they accumulate so much mass in what is, cosmically speaking, the blink of an eye? One theory suggests they were born big, forming from the direct collapse of enormous primordial gas clouds. Instead of a star dying to create a stellar mass black hole, these giant clouds could have collapsed directly into a black hole with a mass of tens of thousands of suns, providing a massive head start. Another possibility is a period of hyper-efficient and rapid accretion, where the black hole fed on surrounding gas at a breakneck pace, far exceeding the usual limits. Or perhaps they grew through a violent sequence of mergers, where smaller black holes repeatedly smashed together, consolidating their mass over time. Some scientists even speculate that exotic seeds were involved, like primordial black holes created in the dense first moments after the Big Bang, or through interactions involving dark matter. The mystery deepens with the observed correlation between a galaxy and its central black hole. The mass of the supermassive black hole is often proportional to the mass of the galaxy's central bulge of stars. This suggests a profound co-evolution, a symbiotic relationship where the galaxy and its dark heart grew up together, each influencing the other's development. The black hole's powerful jets and radiation can heat surrounding gas, preventing it from cooling and forming new stars, effectively regulating the growth of the galaxy itself. To unravel this, astronomers used tools like the Event Horizon Telescope, which gave us our first direct image of a black hole's shadow, and space observatories that peer back in time to the dawn of the first quasars. Understanding the origin of these galactic giants is more than just solving an astrophysical puzzle. It may be the key to understanding how the universe wove its first great structures, the vast cosmic filaments of dark matter and gas that form the skeleton of the cosmos. If black holes were the seeds around which galaxies grew, then their story is fundamentally our own. This intricate dance between the invisible and the visible, between a gravitational pit and the galaxy it anchors, hints at a deeper organizational principle governing the cosmos, one that might be written in the language of the most perfect symmetry ever conceived. This cosmic web is the largest structure we know, a vast architecture of matter and emptiness. Galaxies are not scattered randomly through the void. Instead, they cluster along immense threads, like glittering dew on a spider's web, with each filament stretching for hundreds of millions of light years. Between these brilliant strands lie the cosmic voids, unimaginably vast deserts of near-nothingness that can span hundreds of millions of light years across. This is the true face of our universe, a sponge-like structure of breathtaking scale and complexity. How did we ever map such an immense pattern? The answer lies in ambitious projects like the Sloan Digital Sky Survey, which has meticulously charted the positions and distances of millions of galaxies. By measuring their redshift, the stretching of their light as the universe expands, we can plot them in 3 dimensions. The resulting map is not a random scatter of points, but a clear, intricate network, a cosmic skeleton. The blueprint for this entire structure was written in the first fleeting moments of time. Microscopic quantum fluctuations, tiny ripples in the fabric of reality, were stretched to cosmic proportions during the inflationary period immediately after the Big Bang. These ripples became the slight variations in density that, over billions of years, gravity would sculpt into the filaments and voids we see today. Dark matter is the unseen architect of this web. Its gravity provided the initial scaffolding, creating pools of attraction where ordinary matter, the gas that would become stars and galaxies, could collect. Complex computer simulations show that without this dark matter framework, the universe would be a much more formless place. There simply would not have been enough time for gravity to pull ordinary matter together into such an elaborate cosmic tapestry from a smooth beginning. Yet for all we understand about the dark matter skeleton, the life that springs from it remains a mystery. How does the gas flowing along these dark rivers cool down, collapse, and ignite into brilliant stellar fires? What dictates why one knot in the filament becomes a majestic spiral galaxy and another a featureless elliptical? These are the active frontiers of astrophysics. This grand architecture does more than just host galaxies. It bends the very path of light itself. As light from distant objects travels across the universe, it must navigate this landscape of dark matter. When it passes near a massive filament or cluster, its path is curved by gravity, an effect we call gravitational lensing. This can distort the images of background galaxies into faint, smeared arcs, allowing us to literally see the gravitational fingerprint of the invisible web. Studying this cosmic structure is like reading the universe's deepest history, written in the distribution of galaxies and the bending of light. But within this vast, relatively slow-moving web, there are sudden, violent, and utterly unpredictable events that flash into existence for mere milliseconds, challenging our understanding of cosmic extremes. In the vast, slow-motion architecture of the cosmic web, some events are over in the blink of an eye. From the depths of space comes a flash of radio waves so powerful it releases more energy in a millisecond than our sun does in 3 days. These are fast radio bursts, or FRB, cosmic screams that echo across billions of light years. The first was spotted in data in 2007, a single, blazing spike that seemed to come from nowhere. Since then, we have detected hundreds, each one a brief, brilliant mystery. The most baffling are the repeaters. While most FRBs are one-off events, a few, like the famous FRB 121102, flash again and again from the same patch of sky, ruling out cataclysmic, one-time explosions as their sole source. So what cosmic engine can produce such immense energy so quickly, and sometimes on a schedule we cannot predict? The prime suspects are magnetars, the corpses of massive stars that have collapsed into neutron stars with magnetic fields so intense they could erase a credit card from half the distance to the moon. A starquake on such an object, a sudden cracking of its rigid crust, could theoretically release a titanic blast of radio waves. Other theories point to the violent merger of two neutron stars or a neutron star being devoured by a black hole. Yet the sheer power and repetition of some bursts push the limits of these explanations, leading some to more speculative ideas, like powerful beams from advanced extraterrestrial civilizations. While that remains a remote possibility, the true value of FRBs may not be in their source but in their journey. As these radio waves race across the universe, they pass through the sparse gas that floats between galaxies. This material slows down different radio frequencies by slightly different amounts, causing the burst to disperse, to spread out. By measuring this dispersion, astronomers can count the total number of electrons the signal encountered, effectively using the FRB as a probe to weigh the invisible, ionized matter that makes up the cosmic web. It is like using a single, brilliant flash of lightning to illuminate the entire landscape for a split second, revealing the structure of the fog itself. We have even managed to trace some of these bursts back to their home galaxies, often small, turbulent dwarf galaxies where star formation is rampant and magnetars may be common. Still, the exact mechanism that can pack such phenomenal energy into such a fleeting instant remains one of the most urgent puzzles in astronomy. These millisecond mysteries are a stark reminder that the universe is filled with sudden, violent, and transient events. But if you think a fast radio burst is powerful, it is merely a pop gun compared to the most energetic explosions since the Big Bang itself. If a fast radio burst is a cosmic scream, then a gamma-ray burst is the universe detonating a bomb. These are the most powerful explosions known to exist since the Big Bang itself. In just a few seconds, a single gamma-ray burst can release more energy than our sun will emit over its entire 10 billion-year lifespan, outshining for a brief moment every other star and galaxy in the cosmos combined. We discovered them entirely by accident. In the 1960s, American military satellites designed to monitor Soviet nuclear weapons tests began picking up mysterious bursts of gamma rays coming not from Earth but from deep space. They were random, incredibly brief, and utterly baffling. For decades, their origin was one of astronomy's greatest secrets. We now know these cataclysms are the birth cries of newborn black holes. There are two primary types, each a signature of a different kind of cosmic violence. Long-duration bursts lasting from 2 seconds to several minutes are thought to be produced by collapsars. This occurs when the core of a truly massive, rapidly spinning star collapses directly into a black hole. As it dies, the star launches twin jets of particles and radiation at nearly the speed of light. If one of those jets is pointed directly at Earth, we see it as a blinding flash of gamma rays. The short-duration bursts are even more fleeting, lasting less than 2 seconds. For a long time, their cause was speculative, but a landmark event in 2017 provided the definitive proof. On August 17th of that year, gravitational wave observatories detected ripples in spacetime from a source 130 million light-years away. Just 2 seconds later, telescopes in space observed a short gamma ray burst from the exact same location. This was the collision of two neutron stars, a kilonova. Confirmation was overwhelming. We had witnessed the merger, the resulting blast, and the creation of heavy elements like gold and platinum forged in the cosmic fire. This single event marked the dawn of multi-messenger astronomy, where we observed the universe not just with light, but with the very ripples of spacetime itself. Yet, even with this incredible discovery, fundamental mysteries remain. How exactly do these events channel so much energy into such incredibly narrow, focused beams? The physics involves colossal magnetic fields and relativistic shocks, processes so extreme we cannot replicate them in any laboratory. After the initial gamma-ray flash fades, it leaves behind a fading afterglow visible in X-rays, visible light, and radio waves. This lingering echo allows astronomers to study the burst's environment, tracing it back to distant, star-forming galaxies. Their immense brightness makes them cosmic lighthouses, allowing us to probe the earliest epochs of the universe, back to a time when the first stars were just beginning to illuminate the cosmic dark. These explosions are so powerful, they naturally lead us to wonder about other forms of invisible, high-energy rain constantly sleeting through the cosmos, a silent bombardment from the most powerful accelerators in the universe. This silent, high-energy rain is constantly sleeting through our planet, an invisible barrage of atomic fragments from the depths of space. These are cosmic rays, subatomic particles, mostly protons and atomic nuclei, accelerated to nearly the speed of light. Their energies can be staggering, far exceeding anything we can create in our most powerful particle colliders. A single ultra-high-energy cosmic ray can carry the kinetic energy of a well-thrown baseball, all packed into one tiny, fast-moving particle. The discovery of this phenomenon dates back to 1912, when the physicist Victor Hess took delicate instruments aboard a high-altitude balloon. He found that the level of ionizing radiation increased as he ascended, proving the source was not from the ground below, but from somewhere far above our atmosphere. For over a century we have known they exist, yet we are still hunting for the cosmic cannons that fire them. The lower energy particles that constantly shower down on us have clearer origins. Our own sun is a steady source, and the shock waves from supernova remnants within our galaxy are thought to act as natural particle accelerators, slinging material across space. But the ultra-high-energy cosmic rays, the true giants, are a different story. Their paths are not straight lines. As these charged particles travel across the cosmos, they are twisted and bent by the weak but pervasive magnetic fields that fill the space between stars and galaxies. It is like trying to trace a single raindrop in a hurricane back to the exact cloud it came from. The direction they arrive from tells us almost nothing about where they began. So what cosmic engines are powerful enough to create them? The suspects are the most violent objects in the universe, active galactic nuclei, where supermassive black holes spew jets of plasma, could be one source. Gamma-ray bursts, those unimaginable stellar explosions, are another candidate. Some have even proposed more exotic origins, like the decay of hypothetical dark matter particles. To catch these elusive particles, scientists have built enormous traps on Earth. The Pierre Auger Observatory in Argentina, for instance, is a sprawling array of detectors covering an area of over 1,000 square miles. It does not detect the primary cosmic ray itself, which usually smashes into a molecule in the upper atmosphere. Instead, it captures the extensive air shower, the cascade of secondary particles that rains down from that initial collision. By studying this shower, we can reconstruct the energy and rough direction of the original particle. But to truly pinpoint the sources, we need a better map of the magnetic fields that scramble their trajectories. This search is more than an astronomical treasure hunt. It is a way to probe physics at energy scales we can never hope to achieve in a laboratory, testing the very laws of nature under the most extreme conditions. This quest to understand one type of invisible cosmic messenger naturally leads us to another, perhaps the most ghostly particle of all, one that travels straight to us from the hearts of stars and the ashes of stellar explosions. While cosmic rays are a chaotic bombardment, another form of cosmic messenger passes through you in utter silence and in unimaginable numbers. Trillions of these phantoms, called neutrinos, are streaming through your body every single second, leaving not a trace of their presence. They are the universe's ultimate ghosts, born from the most powerful nuclear reactions. The core of our sun produces them in a constant torrent, and a single supernova can release a burst so immense it briefly outshines the entire neutrino output of every star in the cosmos. The defining feature of a neutrino is its profound indifference to ordinary matter. It carries no electric charge, and it interacts only via the weak nuclear force and gravity, so weakly that a neutrino could pass through a light year of solid lead, a distance of about 6 trillion miles, without a single collision. For decades, this made them nearly impossible to detect. The first experiment, led by Raymond Davis Jr., deep in a South Dakota gold mine, used a vast tank of cleaning fluid to catch a handful of these phantoms from the sun, confirming that nuclear fusion was indeed the solar engine. But neutrinos held a deeper secret. As they travel across space, they do not remain the same. They morph, oscillating between three distinct identities or flavors: the electron neutrino, the muon neutrino, and the tau neutrino. This discovery, which won the Nobel Prize in Physics in 2015, was revolutionary. It proved that neutrinos must have mass, however minuscule, a fact that the standard model of particle physics, our most complete theory of particles and forces, had said was impossible. This tiny mass is a colossal crack in the foundation of modern physics. How can something so fundamental be so poorly understood? The leading idea to explain it is the seesaw mechanism, which proposes that the familiar, lightweight neutrinos we see have impossibly heavy, theoretical partners, perhaps the sterile neutrinos that interact only through gravity. Finding them would open a portal to a whole new realm of particle physics. To catch these phantoms, scientists build colossal traps in the most remote places on Earth. The Ice Cube Neutrino Observatory in Antarctica uses a cubic kilometer of pristine, deep ice as a detector. When a rare, high-energy neutrino from deep space does interact, it creates a flash of blue light that an array of sensitive optical modules can see. This has given us a new way to see the cosmos. In 2018, IceCube detected a single high-energy neutrino and traced its origin back to a blazar, a supermassive black hole at the center of a distant galaxy, shooting a jet of radiation directly at Earth. For the first time, we had pinpointed a source of cosmic neutrinos, confirming these ghost particles as unique messengers from the most violent engines in the universe. Yet the most basic questions remain unanswered. What are their exact infinitesimal masses, and in what order do those masses fall? The answer could determine the fate of the universe on the largest scales, influencing how structures form and how the cosmos evolves. These silent, massless-seeming phantoms, forever passing through our world, may hold the key to physics beyond everything we currently know. That same stellar violence that creates black holes and gamma-ray bursts also forges another marvel of precision. When a massive star goes supernova, its core can collapse not into a black hole, but into a city-sized sphere of pure neutrons, a neutron star. If this stellar corpse is spinning and possesses a powerful magnetic field, it becomes a pulsar, a cosmic lighthouse. Beams of radiation shoot from its magnetic poles, and as the star rotates, these beams sweep across the cosmos. If one of those beams happens to point toward Earth, we observe it as a regular, repeating pulse of radio waves, a blink of unimaginable consistency. The discovery of the first pulsar in 1967 by Jocelyn Bell Burnell was a moment of profound shock. The signals were so perfectly regular that they were initially nicknamed LGM for Little Green Men, a half-serious consideration of an artificial source. We soon realized these were natural phenomena, but their precision remained staggering. Some pulsars spin hundreds of times per second, and their ticking is more stable than the best atomic clocks on Earth. This incredible regularity makes them powerful tools for testing the very fabric of reality. When a pulsar is in a binary system, orbiting another dense star, its orbital dance becomes a pristine laboratory for Einstein's theory of general relativity. The first binary pulsar discovered, PSRB 1913+16, revealed its secrets over years of observation. Astronomers found that its orbit was decaying, the two stars spiraling inward by precisely the amount predicted if they were losing energy by radiating gravitational waves, ripples in spacetime itself. This was the first indirect proof of gravitational waves, a discovery that earned a Nobel Prize and set the stage for their direct detection decades later. Today, we use networks of these cosmic clocks called pulsar timing arrays to listen for the faint background hum of low-frequency gravitational waves, likely generated by the mergers of supermassive black holes across the universe. Yet for all their reliability, pulsars are not entirely predictable. They occasionally glitch. A pulsar's spin, which should be slowing down gradually, will suddenly speed up in a fraction of a second. These starquakes are thought to be caused by dramatic rearrangements in the pulsar's interior. Imagine a crust of iron nuclei, harder than steel, floating on a superfluid sea of neutrons. This superfluid can spin independently, and when its vortices suddenly transfer their momentum to the solid crust, the entire star jumps, causing a glitch. These events give us a fleeting glimpse into matter under conditions we can never replicate, where a single teaspoon of material would weigh billions of tons. The magnetic fields are equally extreme, trillions of times stronger than Earth's, capable of tearing atoms apart. Pulsars challenge our understanding of nuclear matter and the fundamental forces that govern it, pushing the limits of quantum chromodynamics. From confirming Einstein's predictions to guiding us toward a chorus of gravitational waves, these celestial metronomes serve as both timekeepers and probes, their steady pulses illuminating the most extreme physics in the cosmos. Einstein's cosmic drumhead finally vibrated in 2015. After a journey of 1.3 billion years, a ripple in space-time, a gravitational wave, passed through our planet. The source was the final, frantic dance of two black holes, each about 30 times the mass of our Sun, spiraling inward at half the speed of light before colliding in a violent merger. In that last fraction of a second, they released more power than all the stars in the observable universe combined, not as light, but as a shudder in the fabric of reality itself. This wave, detected by the Laser Interferometer Gravitational Wave Observatory, or LIGO, was the first direct confirmation of a prediction Einstein made a century ago. His theory of general relativity told us that massive accelerating objects should produce these ripples, but they were so faint that he doubted we would ever find them. The LIGO detectors are arguably the most sensitive instruments ever built, capable of measuring a change in distance 10,000 times smaller than a proton. They work by splitting a laser beam and sending the two halves down 4-kilometer-long vacuum tubes arranged in an L shape. The beams reflect off mirrors and recombine. When a gravitational wave passes through, it subtly stretches one arm of the L while squeezing the other, changing the distance the light travels by an infinitesimal amount. This creates a telltale flicker in the recombined laser light, a signature that physicists can translate into a cosmic story. That first signal was a perfect match for the computer models of two black holes merging, a chirp that rose in frequency and amplitude before cutting off abruptly the moment the two singularities became one. Since that historic day, we have listened to dozens of these cosmic collisions, not just between black holes, but between neutron stars as well. Each event provides a treasure trove of information that light alone could never reveal. We can weigh the objects involved, measure their spins, and pinpoint their distance across the cosmos. This new sense, this ability to hear the universe, has opened a window onto the dark, violent side of the cosmos, revealing populations of black holes we never knew existed. The future of this new astronomy is even more thrilling. Soon, observatories like LISA will be launched into space, free from the seismic noise of Earth, its 3 spacecraft flying in a giant triangle millions of kilometers apart, will listen for the low-frequency rumble of supermassive black holes merging at the hearts of distant galaxies. It might even detect the faint echoes from the universe's very first second, a primordial whisper from the dawn of time. This is not just a new way to see the universe, it is a fundamental shift in our perception. We are no longer merely stargazers, we are now listeners to the symphony of spacetime, hearing the impacts that shape the cosmos from within the vast, silent voids between the galaxies. We have mapped the glittering filaments of the cosmic web, but the true giants of the universe are the silent, empty spaces between them. Cosmic voids are regions of breathtaking emptiness, some spanning hundreds of millions of light years, where galaxies are almost entirely absent. They are the negative space in the grand cosmic painting, the immense deserts that define the glittering oases. The Boötes Void is one of the most famous, a spherical region so vast that if our Milky Way were at its center, we would not have known other galaxies existed until the 1960s. These voids are not a mistake in the map, they are the majority, constituting most of the volume of the observable universe. But how can such immense regions of nothingness exist? Their origin lies in the primordial seeds of the cosmos. The tiny quantum fluctuations stretched by inflation created not only the dense spots that became galaxy clusters, but also the underdense regions that would become voids. After the Big Bang, gravity began its work, but it worked both ways. Matter flowed out of these low-density regions and into the higher-density filaments and knots, evacuating the voids over billions of years and making them even emptier. It is a cosmic drainage system on the grandest possible scale. While they appear empty to our telescopes, voids are not perfect vacuums. They contain a sparse soup of ionized gas, a faint web of dark matter, and occasionally a lonely dwarf galaxy that failed to be swept away in the Great Cosmic Migration. This lack of mass gives voids a profound influence on the expansion of the universe itself. According to Einstein's general relativity, the expansion rate is not perfectly uniform everywhere. Inside a void where the gravitational pull is significantly weaker, space-time is able to expand faster than in the dense clusters. This means the Hubble constant, the measure of the universe's expansion rate, can have a local value inside a void that is different from the global average. It is a reminder that our viewpoint from within a galaxy-rich filament may give us a slightly biased view of the cosmos's overall expansion. The growth of these voids is also intimately tied to dark energy. As dark energy accelerates the universe's expansion, it encourages voids to grow larger and merge with one another, like soap bubbles coalescing into ever greater empty chambers. By studying the shapes, sizes, and distribution of voids, cosmologists can test their models and measure the strength of dark energy's push. Computer simulations of the universe show this process in action, with voids evolving, stretching, and sometimes even becoming squeezed into a sausage-like shape by the pressure of surrounding filaments. Their existence challenges our intuition. We naturally focus on the bright, energetic objects, the stars and galaxies that fill the night sky. Yet the universe is mostly made of these vast, dark, and quiet expanses. This immense emptiness is as much a part of the cosmic story as any quasar or supernova. It forces us to ask why the universe is structured in this particular way, with its brilliant nodes and its profound emptiness. This very structure, this cosmic web of light and shadow, relies on a universe that is fundamentally transparent, allowing light to travel for billions of years to reach our telescopes. But why is the cosmos so clear? What prevents the fog of the early universe from persisting and shrouding everything in an eternal, opaque glow? The universe was not always a clear window. For hundreds of millions of years after the Big Bang, space was filled with a thick, opaque fog of neutral hydrogen gas. This was the cosmic dark ages, a time when no stars yet shone, and the glow of the cosmic microwave background had faded into the infrared. The cosmos was a shadowy realm, a featureless sea of primordial gas. Then a profound transformation began. The first stars and galaxies ignited, flooding the universe with its first true light. This was not a gentle dawn, but a violent and revolutionary fire. The intense ultraviolet radiation from these first stellar objects began to rip electrons away from the neutral hydrogen atoms, reionizing the gas and slowly burning away the cosmic fog. This was the epoch of reionization, the moment the universe became transparent, a transition that unfolded over hundreds of millions of years, concluding roughly 1 billion years after the Big Bang. We cannot see this era directly yet, but we have clues. The light from the most distant quasars shows a telltale absorption pattern, a cosmic Lyman alpha forest that thins out as we look back in time, eventually hitting a wall of complete absorption where the fog was still thick. The polarization, or the specific orientation, of the cosmic microwave background also carries the imprint of this great scattering event, suggesting reionization was a messy and uneven process. Some patches of the universe cleared early, while others remained shrouded in darkness. What were the primary engines of this cosmic cleanup? Were they the first, extremely massive and hot stars, which blazed brilliantly and died young? or were they the fierce radiation from early supermassive black holes at the hearts of active galactic nuclei? Some theories even suggest a role for exotic processes, like the decay of certain types of dark matter. The upcoming James Webb Space Telescope is our time machine to this formative age. By staring deep into its infrared eyes, we hope to finally witness the first galaxies switching on, to see the bubbles of ionized gas growing and merging, and to understand the precise sequence of events that led to the clear universe we see today. Understanding reionization is more than a history lesson. It tells us how the first structures influenced their entire environment, how energy flooded the voids between galaxies, and how the cosmic web itself was illuminated. This universal transition from an opaque fog to a transparent expanse shows a cosmos in constant, dynamic change, a theme that resonates with an even more unsettling possibility. What if the very rules of physics, the constants we rely on, are not constant at all, but have been shifting since the beginning of time? The bedrock of physics itself may not be as solid as we once believed. For centuries, we have assumed that the fundamental constants of nature, numbers like the fine structure constant that sets the strength of electromagnetism, are truly constant, unchanging pillars of reality. But what if these numbers are slowly drifting, if the cosmic rulebook is being subtly rewritten over billions of years? This radical idea was first pondered by giants like Paul Dirac, who wondered if the gravitational constant might weaken as the universe expanded. Today, we test this by turning the universe into a laboratory. Astronomers analyze the light from incredibly distant quasars as it passes through ancient clouds of gas. The absorption lines in these spectra act as cosmic barcodes, encoding the values of constants like the fine structure constant from a time when the universe was young. Some teams have reported tantalizing, controversial evidence that this constant was slightly different billions of years ago, a whisper of change that, if confirmed, would shatter our understanding. The implications are staggering. A varying fine structure constant would mean that the strength of the forces that hold atoms together has not always been the same. This would violate Einstein's equivalence principle, a cornerstone of general relativity, which assumes the immutability of physical laws. It would point directly toward more complex theories like string theory, where the constants we observe are not fundamental, but are the result of how extra, hidden dimensions are curled up and stabilized. If those dimensions were to shift or evolve over time, the constants would shift with them. To test this closer to home, scientists use exquisitely precise atomic clocks, comparing their ticks over years to see if the fundamental rhythms of nature are changing. They also study the spectra of molecules in laboratories, searching for any drift that might hint at a changing proton-to-electron mass ratio. If that ratio were different, the very size and stability of atoms would be affected, potentially altering the chemistry that makes life possible. This search connects deeply to the mystery of dark energy. Perhaps the cosmological constant is not a fixed number, but a dynamic field whose value has evolved, making the acceleration of the universe a changing phenomenon. The hunt for varying constants is a profound test of our most basic assumptions, a reminder that the universe may be far more fluid and dynamic than we ever imagined, its deepest laws written in sand, not stone. Even the atoms that build our world are playing a cosmic game of hide and seek. We can account for all the ordinary matter, the protons and neutrons that make up stars, planets, and our own bodies, in the early universe by studying the afterglow of the Big Bang. Yet when we take a census of the present-day cosmos, adding up all the visible stars, galaxies, and cold gas, we come up astonishingly short. Roughly half of all the normal matter is simply missing. This is the missing Baryon problem, a glaring hole in our inventory of everything that is. We are not searching for dark matter this time, but for the very atoms we are made of, and they have vanished on a cosmic scale. So where did they go? The leading theory points to a vast spiderweb-like structure known as the warm-hot intergalactic medium, or the WIM. This is a diffuse network of gaseous filaments stretched between galaxies and spanning the cosmic voids. The gas in these filaments is not cold and dense, but has been heated to temperatures between 100,000 and 10 million degrees Kelvin by the shock waves from galaxy collisions and the explosive energy of supernova. At these extreme temperatures, the gas is so thin and ionized that it is virtually transparent, emitting almost no light we can easily see. Detecting it requires ingenious methods. Astronomers use distant quasars as cosmic flashlights. As the brilliant light of a quasar travels through these invisible filaments on its way to Earth, specific wavelengths are absorbed by the hot, ionized oxygen and other elements within the WIM. This creates a unique fingerprint, a set of absorption lines in the quasar's spectrum that betrays the presence of this elusive matter. Space telescopes like Chandra and XMM Newton are also hunting for the faint X-ray glow this superheated gas emits. Slowly, painstakingly, these observations are confirming that the WIM is real, that it forms the reservoir for the universe's missing atoms. Mapping its full extent, however, is a monumental challenge, like trying to trace the outline of a ghost by the slight chill it leaves in the air. Solving this puzzle is critical. It completes the cosmic ledger of normal matter, telling us where the raw material for future galaxies is stored. It reveals the processes that channel gas from the vast intergalactic wilderness into the dense, star-forming hearts of galaxies. This great hunt for hidden atoms has a fascinating parallel in another invisible cosmic structure. Just as we search for the source of the universe's missing mass, we are also searching for the origin of its magnetic fields, a force that stretches across billions of light years and whose genesis remains an enigma. These magnetic threads are woven through the very fabric of the cosmos, an invisible architecture stretching from the heart of planets to the vast emptiness between galaxies. We cannot see them directly, but we detect their presence through the subtle ways they bend and shape light. When high-energy electrons spiral along a magnetic field line at nearly the speed of light, they emit a unique kind of polarized radiation called synchrotron radiation, creating a faint cosmic glow. Another method, Faraday rotation, allows us to measure a magnetic field's strength by observing how it twists the polarization of radio waves as they pass through a cloud of magnetized plasma. These techniques reveal a universe crisscrossed by magnetic forces, with strength ranging from a few microgauss in the deep voids, far weaker than a common refrigerator magnet, to milligauss levels within spiral galaxies, powerful enough to guide the flow of interstellar gas. But where did these immense, pervasive fields come from? One compelling idea is that they are primordial, a relic from the universe's infancy, generated in the violent turbulence of the Big Bang itself, and then stretched to cosmic proportions during inflation. Alternatively, they could have been born from more humble beginnings through a cosmic battery effect. In this scenario, the slow, churning rotation of a vast plasma cloud could generate a weak electric current, which in turn seeds a modest magnetic field. Once this seed field exists, it can be fed and amplified to immense strengths by a dynamo process. Think of the spinning disk of a galaxy as a colossal engine. The turbulent motion of its conductive gas acts like a generator, twisting and stretching the weak seed field, transferring the galaxy's rotational energy into powerful magnetic forces that can then be flung out into intergalactic space. This explains the fields within galaxies, but their presence in the near-perfect emptiness of the cosmic voids is a profound puzzle. How can a magnetic field be maintained in regions so empty that particles barely collide? Some theories suggest that galactic winds, driven by supernova or active black holes, could have blown magnetic fields out into the voids in the distant past, seeding the entire cosmic web. Or perhaps there are mechanisms we have not yet conceived, efficiently generating magnetism in the deepest vacuums. Unraveling this mystery is not just an academic exercise. Cosmic magnetic fields are essential players in the drama of creation. They regulate the collapse of giant gas clouds to form new stars. They guide and confine the paths of those ultra-high-energy cosmic rays, and they influence the stability of galactic disks. Without them, the universe would look profoundly different. As we push our understanding of these invisible forces to the limit, we are forced to consider the existence of objects where matter itself is transformed into entirely new, exotic states, pushing beyond the familiar realm of neutron stars into something even stranger. Even the incredible density of a neutron star may not be the final word in cosmic compression. At the extreme pressures found in the cores of the most massive neutron stars, something even more exotic might occur. The neutrons themselves, unable to withstand the immense gravitational squeeze, could dissolve into a seething ocean of their most fundamental components. This would create a quark star, a hypothetical object where matter exists not as neutrons or protons, but as a free-flowing soup of quarks and gluons. Think of it as taking a neutron star and crushing it until the very identity of its particles breaks down entirely. In this bizarre state, known as a quark-gluon plasma, the individual quarks are no longer confined within neutrons but roam freely in a degenerate fluid. This strange matter might actually be the most stable form of matter in the universe under these conditions, potentially forming stars composed of up, down, and strange quarks. The hunt for these objects is a search for the most extreme state of matter possible before the final collapse into a black hole. Astronomers scour data from unusual X-ray pulsars and supernova remnants, looking for compact objects that seem just a little too small or a little too massive to be a standard neutron star. These anomalies could be the signature of a quark star, an object with a unique mass-radius relationship. Finding one would be a monumental discovery, providing a direct window into the behavior of quantum chromodynamics at densities we can only dream of recreating in particle colliders. It would reveal a new phase of matter and complete our map of stellar evolution, showing the final steps matter takes before vanishing behind a black hole's event horizon. This exploration of ultimate density and the fundamental forces that resist it forces us to pull back and consider the entire cosmos. How did a universe born from such an unimaginably hot, dense state become so remarkably uniform on the largest scales? This remarkable uniformity of the cosmos presents a profound puzzle. Look in any direction, and the faint glow of the cosmic microwave background, the leftover heat from the Big Bang, has the same temperature to within a fraction of a degree. This makes perfect sense for regions that are close together, but it defies all logic for areas on opposite sides of the observable universe. These distant points have the same properties, yet they have been separated by a greater distance than light could have traveled in the entire age of the universe. They are like two people on opposite sides of an ocean who have never met, yet are wearing identical clothes down to the smallest detail. According to the standard Big Bang model, these regions should never have had time to exchange heat or information to achieve this thermal equilibrium. This is the horizon problem, a fundamental flaw in our basic story of cosmic evolution. How can the universe be so uniform when its parts have never been in causal contact? The most compelling solution is a dramatic revision of the universe's earliest moments. Cosmic inflation proposes that a tiny fraction of a second after the beginning, the universe underwent a breathtakingly brief period of exponential expansion, inflating from a subatomic speck to a volume far larger than our entire observable horizon in less than a trillionth of a second. Before inflation, this tiny patch was small enough for all its parts to communicate, to reach a uniform temperature. Inflation then took this small, smooth, thermalized region and stretched it to a cosmic scale, imprinting its uniformity across the entire sky we see today. It was like taking a single, perfectly mixed drop of dye and suddenly expanding it to fill an entire ocean, resulting in a perfectly uniform color everywhere. The mechanism behind this incredible growth spurt is thought to be a hypothetical field called the inflaton. As this field slowly rolled down its energy hill, it drove the repulsive gravity that powered inflation. When it finally reached the bottom, it decayed, dumping its energy into the creation of the hot, dense plasma of particles that would fuel the standard Big Bang. Yet the true nature of the inflaton field remains one of cosmology's deepest mysteries. Is it a fundamental scalar field, a cousin to the Higgs boson, or something entirely different? While inflation is the leading theory, it is not without competitors. The cyclic model suggests our universe is part of an endless sequence of big bangs and big crunches, with each cycle smoothing the universe through a prolonged period of contraction. Other, more speculative ideas have proposed that the speed of light was much higher in the early universe, allowing light to connect distant regions and create uniformity before light slowed to its current value. These alternatives, however, currently lack the robust predictive power and supporting evidence that inflation possesses. The strongest test for inflation lies in the detailed patterns of the cosmic microwave background. Inflation would have stretched quantum fluctuations to cosmic sizes, creating faint ripples in spacetime known as primordial gravitational waves. These waves would have left a distinctive curling pattern, a type of polarization, in the cosmic microwave background. Finding this B-mode polarization is a holy grail for cosmologists, a smoking gun that would confirm inflation's wildest prediction. Experiments are constantly scanning the sky, using incredibly sensitive telescopes at the South Pole and in space, searching for this faint imprint from the dawn of time. Resolving the horizon problem is not just about fixing a mathematical inconsistency. It is about understanding the initial setup of the entire cosmos, the pristine conditions from which everything we see eventually emerged. The same mechanism that made the universe smooth also planted the tiny seeds for all future structure, the galaxies and voids that grew from microscopic quantum jitters. This deep connection between the largest scales and the smallest forces us to confront the ultimate question of why our universe is so comprehensible at all, a puzzle that reaches its peak in the mysterious numbers that define our reality. This final mystery strikes at the very heart of physics, a numerical nightmare that defies all reason. The energy of empty space, the vacuum itself, should be colossal. Quantum field theory tells us that the void is not empty at all, but a seething, frothing sea of virtual particles that constantly pop in and out of existence. When you add up the infinite contributions from all these fleeting quantum fluctuations, you get a theoretical prediction for the vacuum energy density, a number of such staggering immensity it would have curved spacetime so violently that the universe would have been torn apart in a fraction of a second after the Big Bang. Stars, galaxies, and life itself would have been impossible. Yet, when we measure the actual energy of the vacuum through the observed acceleration of the cosmos, the cosmological constant, we find a value that is not just small but almost zero. The discrepancy between the theoretical prediction and the observed reality is a factor of 1 followed by 120 zeros. This is not a small error, it is the most spectacular failure of a prediction in the entire history of science. How can our two most successful theories, quantum mechanics and general relativity, be so catastrophically incompatible on this fundamental point? Proposed solutions range from the elegant to the mind-bending. Supersymmetry, a beloved but unproven theory, suggests every known particle has a superpartner whose quantum contributions could perfectly cancel out the vacuum energy, leaving the near-zero value we see. But we have not found these superpartners, and the cancellation would have to be impossibly precise. This leads many to the stark conclusion of the anthropic principle within a vast multiverse. In this view, most universes have vacuum energy so large they are stillborn. We simply live in one of the rare bubbles where the number is small enough for galaxies to form and life to arise. Other ideas are more dynamic, suggesting that dark energy is not a constant at all, but a field that has decayed to its present low state over cosmic time. Perhaps the most radical proposal is that we are fundamentally wrong about how gravity interacts with the vacuum, that general relativity somehow ignores this quantum froth, a clue that our understanding of quantum gravity is deeply flawed. As we reflect on these 25 cosmic phenomena, from the galactic scales of dark matter to the quantum nightmare of the cosmological constant, a common thread emerges. We are surrounded by a cosmos of profound beauty and even more profound mystery. Each answered question seems to unveil two deeper, more baffling puzzles. The universe is not just stranger than we imagine, it is stranger than we can imagine. This tapestry of enigmas defines the very frontier of human knowledge, a reminder that the greatest adventure of discovery is far from over. These cosmic puzzles are not isolated islands of ignorance, but threads in a single, magnificent tapestry. Each mystery illuminates another, revealing a universe far more interconnected and bizarre than we ever conceived. The relentless push of dark energy, for instance, is not just a force driving galaxies apart. It is a direct confrontation with the cosmological constant problem, a fundamental clash between our understanding of the quantum vacuum and the smooth geometry of cosmic space. They are two sides of the same coin, forcing us to ask what empty space truly is. Similarly, the ghostly presence of dark matter and the hunt for the missing baryons represent a dual challenge to our cosmic inventory. One is the search for an unknown substance that forms the universe's skeleton, while the other is a hunt for the ordinary atoms we know must exist, hidden in a superheated web. Together, they highlight how much of the cosmos remains invisible to our eyes, its full substance just beyond our grasp. On the smallest scales, the spooky connection of quantum entanglement and the fiery paradox of black hole information test the very fabric of reality. They challenge our classical notions of locality and information, suggesting that space itself may be an emergent property of a deeper, more fundamental layer where separation is an illusion. These are not abstract thought experiments. They are pressing problems that force us to reconcile the rulebook of the very small with the physics of the very large. This quest for unification is mirrored in the grandest structures we see. The vast cosmic web of filaments and voids, the great flows of galaxies, are the direct descendants of microscopic quantum fluctuations, stretched to cosmic proportions by inflation. The large-scale architecture of the universe is a frozen record of its earliest moments. Even the most violent and fleeting events, like the millisecond scream of a fast radio burst or the planet-shattering power of a gamma-ray burst, are not mere cosmic fireworks. They are extreme laboratories probing the limits of matter under conditions we can never recreate. They teach us about the lives and deaths of stars, the formation of black holes, and the creation of heavy elements. All of this unfolds within a cosmos whose fundamental constants appear perfectly fine-tuned for complexity. This staggering precision ignites profound philosophical debates, pushing us to consider whether we live in a rare, life-friendly universe among a vast multiverse, or if there is a deeper, yet undiscovered, principle that necessitates such harmony. This beautiful, frustrating interconnectedness is the true state of modern cosmology. Our current models are brilliant, but they are clearly incomplete, patched together to describe a reality that consistently defies our categories. The pursuit of a single theory that can weave together gravity and quantum mechanics, that can explain the universe from its first moment to its ultimate fate, is driven by these 25 intertwined puzzles. Solving one does not simply check a box, it often provides the key that unlocks another, leading us on a continuous journey toward a deeper, more wondrous appreciation of the cosmos we call home. Our journey through the cosmos reveals a universe not of settled facts, but of magnificent questions. Each of these 25 phenomena, from the ghostly tug of dark matter to the violent birth cries of black holes, marks a frontier where human curiosity meets the unknown. They are not merely gaps in a map, but invitations to explore further, to question more deeply. The relentless research into cosmic rays, the large-scale structure of the universe, and the paradoxical nature of black holes continues to challenge our most fundamental assumptions, pushing the very boundaries of knowledge. Let this exploration be a starting point for your own wonder. What cosmic secret baffles you the most? Share your thoughts in the comments below, and subscribe for more deep dives into the mysteries that surround us. Keep looking up, for the universe has only just begun to tell its story.